All right, so let's finish up. This is section 4.6 notes on related rates. Example 8. So in this example, sand is being poured onto a beach, creating a cone whose diameter is always twice its height. So this is one piece of information that sounds like it's important. The sand is being poured at a rate of 20 cubic inches per second. So the cubic inches tells us that that rate is going to be our volume. So dV dt is 20 inches cubed per second. When the height of the conical pile is 6 inches, so there's our snapshot. Our snapshot tells us that height is going to be 6 inches. Let's answer the following questions. Oh, before that. So we said that the diameter of the base, so here's the base, this diameter is always twice its height. So basically the idea is that the diameter is always going to be 2 times the height. Okay? Since we are dealing with volume, and just by looking at question A, you see that it's asking about the radius, we're going to need to deal with radius rather than diameter. So knowing that D equals 2H, we can also say that 2R is equal to 2H. So this might be useful in a second. Okay? And this is given and this is given. So part A is asking how fast is the radius of the pile changing. So it is asking for dr dt question mark. So the first question is all right, what is the general equation that I can use to find dr dt given these pieces of information? And obviously it's going to be the volume equation of a cone. So the volume equation of a cone is going to be V equals 1/3 pi r squared times the height. Now, you notice here that we have 3 variables. 1, 2, 3 variables. And if you remember from optimization, and you can go ahead and try to solve this, but we don't have r and we don't have dr dt. So what we're going to need to do is, or actually we do kind of have r, don't we? How do we have r? Since 2r is equal to 2h, then basically r equals h. So r is 6 inches. So we kind of have r. Okay? And now that we know that r equals h, if I wanted to, I could get rid of this right now and just call that r, just so that I only am dealing with one variable. I could also leave it and just end up plugging in whatever h is. The only problem is I don't know what dh dt. So you'll see that come up at some point. So the best thing to do right now is to use this piece of information, and basically instead of this h, we're just going to write r cubed. And this makes it easier because we don't have dh dt in this problem. So now it's easy to just get the derivative. So we end up with dv dt equals pi r squared times dr dt. The snapshot that we're focusing on is when r is 6, right? Because if h is 6, then r is 6. So we have dv dt is 20 equals pi times 6 squared. We don't know dr dt. You do the math, you end up with dr dt equals 5 over 9 pi inches per second. This is, of course, without a calculator. All right, part B says, how fast is the diameter of the pile changing? So dd dt. Based on the information that we have, and knowing that we need to figure out dd dt, what equation could I use that helps me figure out what the diameter is? Well, we know that diameter is equal to 2 times r. And if I just take this equation and find the derivative of both sides, we end up with 2 dr dt. The reason why I can use this equation is because I literally just found out what dr dt is. Okay? If you wanted to, you could have used this equation and rewritten r as d divided by 2 and gone from there, but it is going to be a longer process. So if this comes into mind, which it should have, this is the equation you would use. So then you solve this. This is 2 times 5 over 9 pi. And so we get our dd dt is going to be 10 over 9 pi inches per second. Part C. How fast is the height of the pile changing? So in this one, our question is dh dt. Okay? So this one, if you remember, h is equal to r, correct? We have this equation. So guess what? dh dt is going to be equal to dr dt as well. And we already have this. So dh dt is 5 over 9 pi inches per second. Easy once you start thinking about these problems. All right, part D says, if the angle of the repose is defined to be the steepest angle at which dry, unconsolidated sediment is stable, what is the sand pile's angle of repose? How fast is it changing? So it's very hard to see, but this is actually kind of already written in here. That this right here is the angle of repose. Okay? So this is the angle of repose. And we are focusing on basically as you're adding. So how is this angle changing? Right? So we're going to be comparing the height to the angle. So if this is the angle, we know that this right here is going to be called the height. And this guy right here is going to be our radius. What do we know about the height and the radius? We know that they're the same. Okay? So, question is, how is that changing? Knowing height and radius. What can we use for a right triangle to compare, to find d theta dt? So looking at this, we have opposite of theta and we have adjacent of theta. So we're going to be using tangent of theta equals opposite over adjacent. Knowing that these two guys are the same, we can rewrite this as tangent of theta equals 1. So now the easy part is, when is tangent of theta equal to 1? That's when theta is equal to 45 degrees, or pi over 4. So this answers the first part of the question. What is the sand pile's angle of repose? When H and R are the same, it's always going to be 45 degrees. How fast is it changing? Well, we know that tangent of theta is equal to 1.